The world is filled with things that we're able to react to and understand without much thought. For example, consider a stop sign that's partially covered by snow. It's still a stop sign. Or a chair that's 5 times bigger than usual. It's still a place to sit. But for computers, who don't have the benefit of growing up and learning the nuances of these objects, the world is often much more messy and complicated. For the first topic, you'll start with a video called Making Sense of a Messy World, where Google engineers and researchers discuss how machine learning is beginning to make computers and many of the things that we use them for, such as maps, search, recommending videos, translations, and so on, much better.
You ready to start right now?
Yeah, thank you.
There have been a number of shifts in the way we think about computing over the past few decades.
The terminology artificial intelligence has come in and out of favor in the scientific community. Sometimes it's called machine learning.
We tend to call it machine intelligence these days.
I just call it intelligence.
And sometimes it's just the effort to build machines that are better.
So in the early days, everything was built on logic, doing mathematical integration problems, playing chess. But we realized that what the real challenges were the things that people can do every day.
The real world is actually very messy. Hard logical rules are not the way to solve really interesting real-world problems.
You have to have a system that'll learn to get the knowledge in. You can't just program it all in.
Artificial intelligence is an effort to build machines that can learn from their environment, from mistakes, and from people.
And we're still at the stage where we don't know what is the right path and the right breakthrough.
So, I mean, there's certainly a whole raft of different approaches.
One of the subfields we call pattern recognition.
Artificial neural network,
Reinforcement learning, for example.
statistical inference, and probabilistic machine learning.
Supervised learning, unsupervised learning. And we're not quite sure what technique is going to lead to better systems. And in fact, it's probably not one technique for everything. It's probably a bunch of different techniques and combinations of those techniques.
Any progress we make in building truly intelligent systems is going to depend on progress in technology generally.
And until recently, we didn't have computers that were fast enough or data sets that were big enough to do that.
And so being able to take a particular problem and spread it out over lots and lots of machines is a very important approach because it makes our research faster.
So there's applications of artificial intelligence around us all the time.
When it begins to work, or it does work, it's all of a sudden given another name.
We're all already using it and very comfortable with it.
Things that now we regard as routine, 30 years ago would have been regarded as amazing examples of artificial intelligence.
Anti-lock braking,
Autopilot systems for planes,
Search.
recommendations.
maps.
To decide whether or not this particular email is spam or not spam.
The ability to translate one language to another with your phone. 10 years ago, if you tried to talk to your computer or to your phone, you know, that would just be hopeless.
We are seeing a steady torrent of these tricks, one after the other, getting figured out right now. And I think a lot of people that are close to the field have this, do have that kind of breathless sense that things are moving quickly.
It's a progressive thing. It's about building things that are slightly better, slightly better, slightly better.
Intelligence is really not going to be something that we ever succeed in defining in a succinct and singular way. It's really this whole constellation of different capabilities that all kind of are beautifully orchestrated and working together.
Predicting the long-term future is very difficult. Nobody can really do it. And the bad thing to do is take whatever's working best now and assume the future is going to be like that forever.
So you've heard a lot about machine learning or ML. Let's start with a definition. What is ML? Here's the definition I like to use. ML is a way to get predictive insights from data to make repeated decisions off of. You do this using algorithms that are relatively general and applicable to a wide variety of data sets. Think of a typical company and how they use their data today. Perhaps they have a dashboard that business analysts and decision makers view on a daily basis, or a report that's read on a monthly basis. This is an example of a backward-looking use of data, looking at historical data to create reports and dashboards. This is what people tend to mean when they talk about BI or business intelligence. A lot of data analytics is backward-looking. Nothing wrong with that. But instead, we're going to use ML or machine learning to generate forward-looking or predictive insights. Of course, the point of looking at historical data might be to make those decisions. Perhaps business analysts examine the data and they suggest new policies or rules. They could suggest, for example, that it's possible to raise the price of a product in a certain region. Now, that business analyst is making a predictive insight, but is that scalable? Can the business analyst make such a decision for every single product in every single region? And can they dynamically adjust the price every second? Now, here's where the computers get involved. In order to make decisions around predictive insights repeatable, you need ML. You need a computer program to derive those insights for you. So ML is about making predictive insights from data, many of them at a time. It's about scaling up BI and decision making. The other part of the machine learning definition is around the use of standard algorithms. ML uses standard algorithms to solve what look like seemingly different problems. Normally, when we think of computers, we think of programs that do different things. For example, the software that you use to file your taxes is very different from the software that you use to get directions home when you're driving. Machine learning is a little different. You use the same software under the hood. That's what we mean when we say ML uses standard algorithms. But you can train that software to do very different things. You can train that software to estimate the amount of taxes that you owe, or train that same software to estimate the amount of time it'll take to get you home. The ML software, once trained on your specific use case, is called a model. So you now have a model that can estimate your taxes, or a model that can estimate the time to get you home. We use the term model because it's an approximation. It's a model of reality. For example, we're giving the computer lots of historical data on drive times in New York City, and it'll learn the relationships in the data, traffic patterns, seasonality, time of day impact, to predict today's commute time home. Whatever the domain, ML modeling requires lots of training examples. We'll train the model to estimate tax by showing it many examples of prior year tax returns. We'll train the model to estimate trip duration by showing it many different journeys. So the first stage of ML is to train an ML model with lots of good examples. An example consists of an input and the correct answer for that input. That's called the label. In the case of structured data, that is rows and columns of data, an input can simply be a single row of data. In unstructured data, like images, an input could be a single image, say like of a cloud that you wanted to classify. Is this a rain cloud or is this not? Now imagine you work for a manufacturing company. You want to train a machine learning model to detect defects in these parts before they get assembled into the final products for users. Well, you could start by collecting a dataset of the images for these parts. Some of these parts will be good. Some of these parts could be fractured or broken up. And for each image, you'll assign the corresponding label. That's the right answer, broken or not broken part. And then use this set of examples as training data for your model. After you train the model, you can then use it to predict the label of images that it has never seen before. Learn from the past, predict for the future. Here, your input for the trained model is an image of the part. Because the model has already been trained, it's correctly able to predict that this part is in good condition. Note that the image here is different from the ones used in our training examples, but it still works because the ML model has generalized. It hasn't memorized the training data, those specific examples that you've shown it, and it's learned a more general idea of what a good-looking part, what the good condition for that part looks like. So why do we say these algorithms are standard? Well, the algorithms exist independently of your use case. Even though detecting manufacturing defects in parts in those images and detecting something like diseased leaves and tree images are two very different use cases, the same algorithm, an image classification network, works for both. Similarly, there are standard algorithms for predicting the future value of a time series dataset, or to transcribe human speech to text. ResNet is a standard algorithm for image classification. Now, it's not crucial to understand how an image classification algorithm works, only that it's the algorithm that you should use if you need to classify images of automotive parts. When you use the same algorithm on different datasets, there are different features or inputs relative to the different use cases, and you can see them represented visually here. You might be asking yourself, isn't the logic different? You can't possibly use the same rules for identifying defects in manufacturing that you do in identifying different types of leaves. You're right, the logic is different, but ML doesn't use logical if-then rules. The image classification network isn't like that set of rules, if this, then that, but a function that learns how to distinguish between categories of images. So even though we start with the same standard algorithm, after training, the trained model that classifies leaves is different from the trained model that classifies manufacturing parts. And guess what? You can actually reuse the same code for the other use cases focused on the same kind of task. So in our example, we were identifying manufacturing defects, but the higher level tasks was classifying images. You can reuse the same code for another image classification problem, like finding examples of your products in photos posted on social media. However, you still have to train it separately for each use case. The main thing to know is that for machine learning, your model will only be as good as your data. And more often than not, you need a lot of data for machine learning. For our example that we talked about, you'll need a large data set of historical examples of both rejected parts and parts in good condition in order to train a model to categorize the parts as defective or not. The basic reason why ML models need high quality training data is because they don't have human general knowledge like we do. Data is the only thing that they have access to learn from.